Now it's recording. Yeah.
Very good. So if all is well, you can see my presentation now. It's still not in presentation mode, but now you should see it in presentation mode. So
Yes.
if it doesn't, then yeah, okay, very good. So our group is a very, very large group, and some of you may know it. It's the Physics of Fluids group at the University of Twente, where I'm working with various colleagues, for instance, Detlef Loze, Michel Versluis, Jacco Snoeyer, and and many others. So you may know some of those names. And this particular project that I will be speaking about today is about the impact of liquids on actually a pretty large scale. Although, yeah, what we're trying to do is to do a synthetic scaling law approach to liquid impact. And I myself, I'm working on fluids. I'm also working a little bit on granular matter and, doing all kinds of different things, especially with bubbles and impact and all these kind of things. So, but I'll leave it here with the introduction and just start with my talk. I would like to acknowledge my co-workers, Anaïs Gauthier and Utkarsh Jain, who have been postdocs and PhDs working with me, and my co-workers, Rodrigo Ezeta and Hannes Bogaert from Marin, and Laurent Brosset from GTT in Paris. So, yes, what I will be speaking about is a synthetic scaling law approach to liquid impact, and actually the motivation to look at these particular kinds of things comes from the energy transition, where we move from traditional fossil fuels like diesel and coal and these kind of things to more renewable types of fuels like methane or hydrogen. And these more renewable fuels are most efficiently transported as cryogenic liquids, and you can do so in a truck. Can you, by the way, see my mouse when I'm pointing?
Just moment. Yes, I can see it. Yes.
Very good. Okay, so that can happen on a truck like this one over here, or in large vessels like the ones to the left and to the right, in which they are transported over sea. And in order to do this transport, the industry needs to deal with sloshing. And it's well known that the container load in liquid transport is almost exclusively caused by sloshing wave impact. And therefore, one needs to predict container load. And in industry, there are actually two ways to do that, and also in academics related to that. There are two ways of doing that. One is by doing experiments, and necessarily these experiments are at a strongly reduced scale. Like, for instance, here you see a sloshing model test on top of a hexapod. The hexapod is there to mimic the motion of the ship on the sea. And in all of these experiments where you measure the pressure in these liquids over here, which typically are not LNG, of course, because that would be a bit hard to do. And it is unclear if and how the model results that you produce from such an experiment can be carried over to full scale. And to put it in terms that the engineers put it, the key engineering question is whether conclusions based on reduced scale experiments are conservative, meaning that the load that you measure in a small scale experiment, if you scale it up to the full scale, is it then a good representation for the loads that are actually experienced in full scale? And especially, are they not smaller than that? Because if the real loads are larger than the ones that are predicted, then we are in trouble as an engineer, of course. Good. So that was one of the approach. The other approach is numerical. But if you do direct numerical simulations of these huge systems, then that would be highly expensive, and resolving all relevant scales simultaneously is almost impossible. So, in conclusion, model experiments, it's unclear how results carry over to the full scale. For DNS and other numerical approaches, they're often way too expensive, especially if you want to do very, very long series with many, many impacts, if at all feasible. And therefore, we do a new synthetic approach where we use scaling laws to introduce physics at any scale. Good. And the key question we want to answer is how to estimate the pressure map P as a function of spatial and temporal coordinates during these impact events. And well, as an example, we will take a few experiments that are well known to you, like droplet impact, the one that you see here on the top, and wave impact of waves generated in a flume, that you see here in a 1:6 scale experiment and in a full scale experiment. And yeah, and if we look at these different examples, they are characterized by a length scale, which is the radius of curvature at the point of impact, and by the impact velocity with which the liquid mass impacts onto the solid. And then for these three examples, R0 ranges from about 3 millimeter for the droplet to about a decimeter for the full scale experiment, and U0 ranges from 1 to about 10 meters per second. Good. The simplest answer that we can give to the question how the pressure map looks is, of course, that it should scale as the inertial pressure rho L times U0 squared. And well, if we concentrate ourselves on a 2D system, non-dimensionalize spatial coordinates with R0, time with R0 over U0, and pressures by the inertial pressure scale rho L U0 squared, then well, we get a dimensionless representation of our particular problem. And well, note that I denote the dimensional quantities by a little tilde on top. So usually if there's no tilde, then these are dimensionless quantities. Now, the very first thing that one thinks about when the liquid mass impacts the solid is the incompressible response of the liquid, also known as the Wagner problem. And this, well, this is a very simple representation of the result of this, of the pressure in the map that we get with this Wagner problem, where at time t is 0, we get a singularity at x is 0, and then as time progresses, the pressure profile spreads in time, and it produces this double-horned profile that is very well known. And well, I put some references by these things that I discuss here, but by no means I want to say that this is the main result from that particular paper that I refer to here. There's much more in that paper, and the paper is just there to give you more or less the current state of the art of these type of problems. So, well, that is one thing that can happen, the incompressible liquid response. But, well, of course, if a liquid hits a solid, that always happens in an atmosphere, and that atmosphere that interferes with the impact of the incompressible liquid. So we have also a response from the gas phase that is in between, and that I will call the incompressible gas response, and it's also well known as the air cushioning response. And just by solving for a liquid mass with a radius of curvature R0 that hits a solid wall, we can just, for the very last instances, solve the lubrication equation in between, and then we get the following expression that you see over here. And then if I plot that expression, what you see is that it corresponds to a pressure peak that becomes ever narrower and higher in time as we approach the impact. And note that tau here is the amount of time that is still remaining until impact. So important in this solution is a dimensionless number, which I've called K. You could see it as an inverse Stokes number, or as the gas to liquid density ratio divided by the Reynolds number in the gas. That's what it is. But yeah, so it becomes narrower and higher in time, and you do not see the narrowing so much. But if we divide all pressure profiles by the maximum pressure, then you see that indeed, as time progresses, the peak becomes narrower and narrower. So we now have two phases, and that's the incompressible air phase and the incompressible liquid phase. And well, what will now happen when the liquid approaches the wall? Then, of course, the softest material will start to yield. So the air will start to yield first. And then when pressures are large enough in the air layer, then also the liquid will start to yield, and well, that's the way this impact will progress. But of course, the question is, what determines the transition from the incompressible gas to the incompressible liquid response? And the idea is now that the transition happens when there is the same forcing on the same area. And for that, you need to realize that the pressure in the gas becomes larger and larger and on a narrower and narrower area as we approach the impact. And then at some point, it becomes so large and so narrow that it becomes comparable to the Wagner pressure at the same size and in the liquid. And then, of course, what will happen, because then in the air phase, the pressure would rise more and more if there wasn't the liquid phase, but then the liquid will start to yield, obviously, and we will get the Wagner response. To put this a bit more quantitatively, what we can do is we take the width of the air cushioning response and the width of the Wagner response, that's over here. We equate the two. That gives us a link between the time variable tau and the time variable t. And then we can solve the central pressure here. I take the central pressure, so of the two profiles, as a function of tau for the air cushioning pressure and as a function of w for as a function of t for the Wagner pressure. And that gives us a unique solution where the pressure in the air phase is exactly the same and on the same scale as in the liquid. And then, of course, what happens is that the pressure will rise in the air cushioning phase, and then we will hit this value here, and then we'll instantly jump to that over there, and then we have a Wagner response for the rest of the time. So it looks more or less like this. So here's the rise, and here the decay that happens afterwards. And I made a little animation of this. So here you see the air cushioning pressure forming in the system, and now it jumps over to this Wagner pressure, the double-horned pressure profile that happens later. Good, and well, what I did here is I equated, I jumped when the central pressures were equal for the air cushioning and the Wagner profile, but I can also take another, of course, another kind of rule to jump from one to the other. So for instance, I can take equal forces where the integrals under the two curves should be the same at the moment that I cross over from one to the other. And you see that there is little difference on what precise criterion I'm taking. Good. Is there any evidence that it actually happens this way? And well, in fact, there is. So this is a very nice paper by Ross and Hicks, where they look at the impact of various different liquid shapes onto a solid. But this is for a I don't remember whether it was a sphere on a horizontal liquid or the other way around, a solid sphere on a liquid, or a liquid droplet on a solid. But on the left, you see the Wagner response, with the horned shapes that you see over here, and this is an analytical solution in the lubrication approximation. What happens if you take the air phase into account, and then you see that here the air cushioning pressure develops, and then at T is 0, it crosses over to a more Wagner-shaped intermediate profile until at T is 4, dimensionless time, of course, you cross over to this one-horned peak. And also from our own work, we looked at boundary integral simulations where we had a lubrication layer for the gas in between. And these are, by the way, two liquid objects, so a liquid droplet impacting on a liquid surface with air in between, but it also holds for a solid. It gives you exactly the same result. And here you see the corresponding pressure. So this is the approach of the liquid. Note that the vertical length scale is very different from the horizontal length scale, such that you get a very different, a very oddly shaped circular object, but it's more or less circular. So and here you see the pressure in the gas, in fact, or the pressure on the interface. And the pressure in the gas has this typical air cushioning shape at this point in time, and then as it approaches, it crosses over into this Wagner profile. So in both cases, we indeed go from an air cushioning response into such a Wagner response. Just like quite similar to what we have done with our two simple analytic expressions. Good. Now let's add another phase to it, and let's look at the compressible liquid phase. So this was analyzed quite some time ago by Lesser, and basically what he did, he let the droplet impact on the solid, and then on a time scale where the liquid would not be able to move yet, because simply all motion would have been too quick, he assumed that the liquid would get pressurized, that there would be a pressurized region forming that looks like this here, and that would basically be created by infinitesimal pressure waves emanating from the different points on the surface as soon as they are touched. And he was able to determine the pressure on the interface as a function of the position along the interface in a parametric way. And it's this a little bit complex looking formula over here, where RC is the radius of curvature, and which is even more complex looking, so I didn't reproduce it here for you. But what is important to note is that M is the Mach number, and so here we see a function of the Mach number, and T is time, and S is also a time-like parameter that both are limited by m squared over 2. And if we plot the pressure profile as a function of time, we see that it emanates from zero, from position 0, and then it broadens in time. And as time progresses, it produces this singularity at the ends. And the singularity, the divergence, occurs when the rim velocity becomes sonic. And that's the condition, of course, that the derivative of the rim position with respect to t is equal to the speed of sound in the liquid, and from that we can find that the time at which this happened is given by the expression here, which, when non-dimensionalized, corresponds to 1/2 m squared, which gives the limit for which this expression is valid. Now, the divergence at Tc is, of course, because of constructive interference of all these infinitesimal waves here when the rim velocity becomes sonic. And in reality, what will happen is that the liquid in the rim will start to move at its very last moment in time. Good. So now we have 3 phases. We have the incompressible gas phase, we have the compressible liquid phase, and we have the incompressible liquid phase. And then, what will happen is similar to what I've shown you before. So the softest material will yield first, so that is the air, and then until pressures become large enough to trigger a compressible liquid response, that will then happen without anything moving, of course, because that is the phase in which the liquid is being pressurized, and a shock wave is moving, you could say, but further nothing is moving. And then finally, the liquid will start to move as well. So we get an incompressible gas response, then a compressible liquid, and an incompressible liquid response. And then, of course, we can do the same thing as we've done before. We can find ways to move from one type of response into the other. So here it's from compressible liquid to incompressible liquid response. And what you see here is that, what I've taken is just that the compressible liquid will continue with the incompressible liquid response on the same support, basically the same width. And there is a pressure jump between the compressible liquid and the incompressible liquid response, but that could be realized to be due to the sudden pressure increase because the liquid, in fact, starts to move at that point in time. And well, for the transition from incompressible gas to compressible liquid, we have a similar type of criterion as we also had for the incompressible gas to the incompressible liquid response. Now that's very similar. So we just look when because the pressure in the incompressible gas phase narrows and steepens. So we look at when the pressures and the widths are similar in the incompressible gas and the compressible liquid response. Good, but then of course it could be that with this last transition the rim velocity is already smaller than the speed of sound. So what if we compute that the rim velocity would be smaller? Then an incompressible liquid response, a compressible liquid response, sorry, will of course not be possible now because, well, the liquid will immediately start to move. And this means that depending on the initial conditions, we can either have we can either have or not have a compressible liquid response. And here you see basically the phase space spanned by the radius of curvature R0 and U0, and these are pretty large numbers. So U0 goes up to 10 meters per second, which is still okay, but R0 goes up to 10 meters. So that's maybe a little bit exaggerated for these type of systems. But yeah, you clearly see that there is a phase where these simple scaling laws predict that there is a compressible liquid phase, and where the simple scaling laws predict that there is no compressible liquid phase. And then if we look at the experiments that I've shown you in the introduction, so the droplet impact and the small scale liquid impact, they are both very much in the no compressible liquid phase. So yeah, for basically air and the typical liquids that we use in everyday life, we would not expect a compressible liquid phase for these type of impacts. And the only case in which we may expect such a compressible liquid phase is the one at the very highest scale, because that is in there, but there are also additional things happening over there that makes it inconclusive whether such a compressible phase will occur, but it could occur in any case. So this is the first conclusion that I want to draw. So a compressible liquid phase may only occur for a sufficiently large radius of curvature and impact velocity. Now, I show you a sequence of pressure signals starting from the same initial condition, but I incorporate different response phases. So this is just the incompressible liquid response. Now you see that it comes out from the center and then moves out towards the sides. Then I can add the incompressible gas response, basically the animation that we've seen before, incompressible gas and incompressible liquid. Here we jump over from one to the other. It happens just outside of the field of view. Then here I have the compressible liquid and the incompressible liquid, so without the incompressible gas response. So you see here the sudden jump to the Wagner response, so from the lesser compressible liquid response to the Wagner response. And finally, all three together, and that's what you see happening over here. So we see the incompressible gas response, which now changes into the compressible liquid response. And now we get a jump to the incompressible liquid response. So I play those four movies once more, but all together now, and I would want you to look at the pressure that occurs in the center. And that happens now. And I want you to focus on how high it comes. And probably you will have seen that it really comes the highest, of course, in the incompressible liquid case. No, because there we have a singularity at T is 0. So, and the more other things we add, the less it seems to become. So what I do here is I compare the central pressure as a function of time. This is for only incompressible liquids. So I basically jump up to infinity over here and then slowly go down as 1 over T as it comes out from the formula. And well, if I add the incompressible gas response, then I see that here is the incompressible gas rising. I do not reach a singularity, but At this point, it crosses over to the other one, to the incompressible liquid response. Then I can do the same thing for incompressible liquid and compressible liquid. So here we have the compressible liquid response, and then here it jumps over to the incompressible liquid response. And then finally, I have all four of them, the incompressible gas, compressible liquid, and the incompressible liquid response. And what we very clearly see if we look at the maximum pressures that we reach is that the Wagner response is the worst case scenario that one can get and is typically mitigated by the other effects that we include. Good. So, well, if we make a little list of physics to include, then well, we can think of the different properties of the liquids and gases that are being at play. So we have included the incompressible liquid phase, we have included the incompressible gas phase, and the compressible liquid phase. So those three are basically now included. But there are more things that one could put on on the list. So there is a compressible gas response, also known as a Bagnot response. There is basically the viscosity of the liquid that may play a role, and there are possible instabilities like the ones that you see occurring here in the full scale. You see that it's very rugged at the interface. So those instabilities could definitely play an important role. And well, what I put also next to it is basically the governing dimensionless variables that correspond to each of those. So the Fruit number and the density ratio for the incompressible liquid response, this K number that we have already introduced for the incompressible gas, so the inverse Stokes number, the Mach number in case of the compressible liquid, the Euler number, P naught over rho L U naught squared for the compressible gas, the Reynolds number in the liquid for the liquid viscosity, and well, the Kelvin-Helmholtz instability appears to be mainly determined by the Weber number. And then there is also phase change. I won't be speaking about that, but definitely that would also be something that needs to be taken into account when dealing with liquids like LNG or liquid hydrogen. Good. So let's spend a few words on the stability of a diverging Kelvin-Helmholtz flow. So basically, if you have such a liquid that impacts onto such a solid wall, then what happens in the very last stage is that, well, this air pocket is being compressed by the liquid moving. This crest over here is about to impact the wall over here. And then what you could say is that there is a volumetric compression of the gas pocket due to these velocities over there. That leads to a more or less constant volumetric gas flow rate in the neck. At least it shouldn't, because it simply depends on the volumetric compression of this gas pocket. It shouldn't depend too much on time, especially not if you compare it to the size of the opening that you have over here. So the volumetric flow rate is more or less constant, and that means that you get a diverging gas flow in the neck. So basically, UG is just this Q naught divided by this little bit over here, which you can write as U naught times tau, where tau is the amount of time remaining until impact, so T impact minus T. And then what you can do is just do a stability analysis of the interface here. So you have a gas flow over there, which depends on time. Your liquid is quiescent initially. Well, we have, of course, the density of the gas and liquid, the surface tension, and we could have an acceleration like the acceleration of gravity, which, well, for this particular case, we'll put it to 0. And then you can just do a modal analysis where you have a deformation of the interface epsilon of x and t, which can be written as eta of t times e to the ikx. And well, and then you can, with k, of course, the wave number, and then you can derive the following equation. This was already done by Kelly about a lifetime ago. It's actually pretty exactly my lifetime ago, my birth year when he did this. Well, what I can do is assume that rho g over rho l is small, such that we get rid of all of these density terms over there, and then it looks a little bit more benign. So, well, we have basically an amplitude equation, second order, with stabilizing gravity term, a stabilizing surface tension term, and a destabilizing gas term, and it looks exactly like the Kelvin Helmholtz problem, with only the difference that that UG is now a function of time. And of course, delta is rho g over rho l, and that is assumed to be much smaller than 1. And if we plug in this functional form for UG of t, we get the following amplitude equation. And well, if we take that amplitude equation, I just reproduce it over here and use water and air at standard conditions and plug in that G is equal to 0 because it's a horizontal impact of a liquid mass, and then solve the equation for each wave number, then we can determine the onset time. So basically the time at which the amplitude starts to diverge. So basically the amplitude of the solution of this amplitude equation starts to diverge. And then, well, if you would do it classically, so if you would neglect the fact that you're dealing with a time-dependent equation and would completely neglect the time dependence, then the conclusion would be pretty similar to the conclusion that was taken from a standard Kelvin-Helmholtz constant gas flow type of analysis, namely that if you don't have any gravity, then large wavelengths are always unstable. And that's what you see over here as well. So actually all wavelengths are unstable. Only the smallest wavelengths, they are less unstable, you could say, than the largest wavelengths. However, if you include the time dependence in the analysis, so solve the full equation and not only look at something like a frequency and what it depends on, which was the classical way of looking at it, then you see that that large wavelengths are being stabilized, and that in fact you get a marginally stable wavelength, and which is given for the different parameters over here. They lie on this particular curve over here. Of course, well, you can predict marginally unstable wavelength, and the onset time from this, I should have said, from this maximum. No, so basically this is the point that becomes unstable first. So that is the wavelength that you would expect to see in an experiment. And well, you can deduce these expressions over here, where the marginally stable wavelength is given by this expression over here, linearly in Q naught over U naught, which is also a length scale, of course, and this is the onset time. Now, what would such instabilities have for effect in the pressure map? And well, what will happen is, of course, that there is a corrugation of the interface, as you see happening over here. And so this is the original smooth object impacting, and then instabilities form here in the neck region, and then from that we see that there will be a typical wavelength and a typical amplitude, and that will lead to a different radius of curvature in this region over here. And typically you have a radius of curvature R0 star that is, well, if this is a sinusoidal shape, then it would have this particular form, and typically that would be much smaller than the original radius of curvature R0. So, well, if we now use U0, the impact speed, and this smaller radius of curvature due to the instabilities as an input for the pressure map, and just plug it in, and if I just look at the Wagner response and to the influence that it has over there, now if we take the central pressure of the Wagner response, then it's just 1 over the square root of T in dimensionless in dimensionless terms. And if we make that dimensional, then we see that the central pressure non-dimensionalized with rho L u naught squared is just the square root of R naught over u naught times T in dimensional units. And then if we do the same with instabilities, the expressions are of course exactly the same, only instead of R naught, we now have R naught star. So the pressures that we get with instabilities and the pressures that we get without instabilities can be related very simply from this expression over here as that the pressure with instabilities is the square root of R naught star over R naught times the pressure without instabilities. And that, of course, since R naught star is smaller, typically much smaller than R naught, this one will be much smaller than the original pressure. So what instabilities do is distribute the pressure over a larger surface area while keeping the total force approximately constant. And now to that the force is approximately constant, you can realize if you look at the width of the pressure signal. Also in the same way, this is without instabilities in dimensional terms, this is with instabilities. And then we see that the width of the profile also scales with the factor R naught star over R naught times the width without instabilities. And therefore, if we multiply the two to get the force, we get basically that the force with instabilities is R naught star over R naught times the force without instabilities. And then if we sum over each of the different crests that we have, then we will get something that would be similar on the left-hand side as it is on the, that would be similar as it is for PW. So that's basically a very handshaking proof that, well, it's not a proof, argument that that the pressure just distributed over over the different crests in the instability. Good. So I don't know what happened now because this is somehow coming. We already saw this, so this, sorry about that. There is I went back somehow with the slide. So here we continue. So how much time do I still have? Sasha?
At the moment, it's 10 minutes, at least 10 minutes.
At least 10 minutes. Okay, then I can also say something about the two remaining things that we haven't discussed yet, namely liquid viscosity first and the Bagnall problem, compressible gas response on the other. So liquid viscosity has, of course, an influence where liquid is moving. No, so and that is, of course, during the incompressible liquid response. And then if you look at what mainly is happening when such a liquid object with a certain radius of curvature is impacting a solid wall, is that it bends around like this. The liquid will bend around over a typical distance delta x, and this delta x is of course, is of course related to where you see a peak in this typical Wagner horn, if to call it that way, or the Wagner peak that is on both sides of the pressure pulse. And then if you just take Navier-Stokes and you just approximate the acceleration term by the fact that you need to bend this liquid around the corner, so you then get rho L times u naught squared over delta x, since it needs to bend around the corner over a distance delta x, then that would be similar to delta P over delta X. That will be typically the change of pressure over this distance delta X. And then we, of course, have the viscous term, which we can estimate as mu L times u naught over delta X squared. And then in order for the pressure to accelerate the flow, we need the first and the second term to be approximately the same. So we need the third one to be much smaller than rho L times u naught squared over delta X. And then if we take, we can then of course solve for delta x. So delta x needs to be much smaller than the liquid viscosity, dynamic liquid viscosity over rho L U naught. And well, inserting that in our approximate equality then gives that delta P over delta X should be much smaller in order to have this inequality holding, should be much smaller than rho L squared times U naught cubed over mu L. And then if you make this dimensional expression dimensionless, then you find that delta P over delta X must be much smaller than rho L nu naught times R naught over mu L, which is just the Reynolds number. So what we need is that the pressure gradient is limited by the Reynolds number in the liquid. And so it will basically cut off the horns. This is maybe a bit exaggerated like this, but it will essentially just cut off the horns of the Wagner profile simply because it wouldn't allow for such large pressure gradients to exist in a real flow. So pressure gradients are limited by viscosity. And then for gas compressibility, we have the so-called Bagnall model, and Bagnall model is a very simple model where you have a gas pocket that is compressed by a liquid piston, or it could also be a solid mass. The original problem was formulated with a solid mass, but it doesn't matter that much what you take, whether it's liquid or solid, as long as it doesn't move. And then, of course, you can write down an equation of motion for this liquid mass as it compresses with a velocity v, this gas pocket over here. Now, you can also think of this case as an air pocket that is essentially caught on a solid wall within a flow. And then if that happens, and if the air pocket doesn't move, then you could say that the bubble is pressurized by motion in the x direction. So essentially, when this bubble here is compressed in the x direction, then the pressure would be something like the pressure on the other side times x naught over x times gamma. That's just the adiabatic compression law, assuming that this all happens adiabatically. And then the bubble inertia in this problem is, of course, provided by some added mass term that depends on the shape of the bubble, obviously, but we have like an added mass coefficient times L naught square. Note that this is, of course, a two-dimensional problem, and therefore, it's L naught squared times rho L. And the bubble experiences a quadratic drag because, of course, you have this liquid flow that will flow around this bubble as this air pocket is caught on the wall. And we have a drag coefficient times rho L L naught times a velocity squared. And well, we can just plug all these terms together in an equation of motion that you see over here. And this equation of motion we can easily non-dimensionalize. And what you see is that, well, it looks like this if you do it with the dimensionless parameters that I've written over here, which are the same as I've used all the time, with the only exception that now R naught is replaced by this initial size of the bubble x naught in the horizontal direction. And with these boundary conditions over here, dimensionless, and you see that there are only two parameters in this system. There is the ratio of the two, of the added mass and the drag coefficient times L naught over x naught, which is of order 1. And the second is just the Euler number divided by the drag coefficient, which, well, the drag coefficient will also be of order 1 probably, and therefore will be approximately equal to the Euler number. And then these are just some examples of what you get when you solve this equation for different impact velocities. Here I took the same values of x naught and L naught, but different impact velocities. So here it's 1 meter per second, and here it's 3 meters per second. And you see that you get something like a damped oscillation, which is typical also for what is found in these wave impacts. Good. So this is the end of my talk. So we strive to understand liquid impact phenomena using a synthetic scaling law type of approach. A compressible liquid phase only occurs if we have sufficiently large impact speed and radius of curvature. Then the incompressible liquid Wagner response constitutes the worst case scenario and is typically mitigated by other effects. And instabilities mitigate impact by distributing pressure over a larger surface area. And well, this is what I wanted to say. I thank you for your attention. And I want to make a little bit of an advertisement for Multiphase 2022, which is a conference which concentrates a lot on multi-phase impact problems, which will be in September 21 to 23 in the Wick Hotel in Wageningen in the Netherlands. So if you're interested, just send an email to multiphase 2022 at marin.nl for more information, or well, you can also drop me an email, or you can immediately submit an abstract. Good. So that is what I wanted to say, and I thank you for your attention, and I hope that you have some questions for me.
Thank you very much. Thank you, Devaraj. Thank you. Very interesting. And I understand you solved just one equation at the very end, and all other things you managed to estimate. And
Exactly. Yeah.
But still, I found there are many interesting, not just interesting, important conclusions. In particular, you mentioned that as far as I understood, that even we include different effects into the model, it's likely that they say total force will be the same.
Yes.
So that's what I understood. So some like instability, gas, it's make the contact region larger, but at the same time pressures are lower. So that is very interesting idea. Hopefully there could be some, I don't know, simulations with CFD or something about it. Indeed,
Yep.
It's looks the case, and if it's right after multiple confirmations, then it could explain the applicability of a simplified model, very simplified model, which still gives very useful results. So that is the.
Yeah. So yeah. So what I wanted to say is thank you very much for your short summary of basically what I said. Yeah. So the idea that we have with this is that also if you for instance that you have experiments on a smaller scale, that you are now better able to say how these pressures that you measure on the smaller scale, how they would carry over to the full scale. No, just not that the simple models that I use here, that they will give you an exact answer that is perfect up to I don't know how many decimals. That's definitely not true, but that it will give you a handle to basically translate in a better way the model experiment results to the full scale.
Yeah.
That's the idea.
Yeah, exactly. So the questions from our participants, not many. So okay, Peter, could you? Yes.
Thank you, Sasha, and thank you for the very nice talk. I wanted to ask about the relative importance of gas compressibility and liquid compressibility, and just exactly where in sort of the regime diagram, the phase space of R0 and U0, we're going to have impacts which have compressible liquid, but still have incompressible gas. Because I would have thought gas would have compressed before you compress the liquid.
That's a very good point, of course. Well, of course, the gas would already have compressed to as far as it would be important. So this is really when almost all of the gas has been squeezed out from the gap. No, so it's then you will see that that you get something like a lubrication approximation, and yeah, where basically the compressibility of the gas is not relevant any longer. No, so because viscosity is then so very important, and it essentially just is a solid for all practical purposes almost.
But I mean, there are
understand?
lubrication models which do include gas compressibility in there.
I could do that, but no, it doesn't include it. No, so it's just a simple lubrication model without gas compressibility included. Yeah.
Thank you.
So far, no other question. Yeah, okay, Javier, please. Javier.
Yeah, let me connect my camera mic. Yeah,
Yes.
thank you very much, Devaraj. It's a lovely talk. I think I heard an early version some time ago, but I can tell
Yes.
it's now richer and contains more effect. It's really nice. Thank you very much. Yeah, I had a few questions that come from the solid side. No, so one of them I noticed in the full-scale experiments, the wall is corrugated or it has some sort of pattern, right?
Yes.
Yeah. So I wonder if I mean, how do you calculate the wavelength that you want to give to this wall, and if it's connected somehow to this Kelvin Helmholtz instability? Like, you know, because I could imagine that in principle the corrugation of the wall could play a similar role on spreading the pressure force as the Kelvin Helmholtz instability, right? So I wonder if there could be some sort of connection between the two ideas.
Yeah, I think that's a very good point. Well, there are multiple aspects to your question. First of all, I neglected the solid at all completely in my talk. No, and obviously, one could think of including the solid in a similar way. No, that you basically say, well, you just look at which part of the system is the most is the softest. No, and that starts to respond first. But yeah, at some point. Then the solid may become the softest part in the whole equation and will start to yield at some point in the whole process. So it could be included like that. Then, well, about the corrugation is there because it's there in these large ships where you transport LNG. Because, well, obviously what happens is you have a system that is partly cooled down to 111 Kelvin and partly at, let's say, about room temperature or so, or sea temperature. And of course, the structure that you contain your liquid in needs to be able to withstand these changes in temperature. So they're basically there to be able to expand without the whole thing bursting apart, because that would be really bad. So that's the reason why they put these corrugations in. And well, when I'm thinking about the Kelvin Helmholtz instability of the interface over here, I'm not predominantly thinking of this corrugation here, because that would then have again another effect and it should again be modeled in a different way. But yeah, it could indeed also be treated in a similar way. That's
Thank you very much.
Yeah. Thank you. Anybody else? Yeah. As to that device, that instability, it's a very interesting analysis. But the formula for velocity in the gas you showed actually goes to infinity, 1 divided by tau there.
Yes.
But it seems that, as far as I remember, in the model of that air cushion model with compressibility, the velocity at the outlet from the cavity, it's limited to the sound speed. So it cannot be very high. And this means there is a certain limit to your wavelength.
Obviously, yeah. That's a very good point. Yeah, that's a very good point. So of course, yeah, this can only hold as the gas speed is not moving over the speed of sound in the gas. That's obviously the case. And if the speed of sound in the gas would already be attained before the instabilities arise, then this will interfere with, of course, the whole stability analysis. No, because then one couldn't do a similar stability analysis, and one needs to take into account the compressibility of the gas in that case. However, one can show that this is not very likely to happen for practical systems. So usually the instability will occur much earlier than when the gas speed becomes sonic. And then, of course, well, once the instability has occurred, is the linear stability analysis is only gives you, of course, that the instability occurs, but not how the instability grows. Now, then you really need something more evolved than just a simple linear stability analysis.
And from that point of view, so this instability is leading to something, and that something, I believe, it's mixing. So the gas and liquid, they mixed in that region, and potentially in modeling or in experiments, if we have a chance to focus on this region, we can expect kind of that mixture, so another fluid. So this is a little bit about your phase change part of your talk. You did not cover, but it's always there. And so is it possible? Do you think possible in experiment? Okay, it could be possible, but how to do this in experiments, in calculation, to account for mixing?
Yes, I think that's a very good point, and indeed we're working on, but this is all preliminary still. We're working on adding in simulations, in experiments, on adding like gas bubbles to the flow, gas or vapor bubbles. No, vapor bubbles would be relevant for the LNG system, and to see how the presence of these bubbles, how they basically interfere with the pressure map. And that's a
very interesting. Very interesting. And also, it's Peter, do you have another question?
If that's okay, Sasha, do you want to? Well, I can go now. Or do you want to continue? I have a question. So in this instability, when you have these multiple impact sites, in order to assume that your sort of the global load is the same as a sort of single impact site, you've assumed that every local impact site is essentially a micro image of the Wagner impact problem.
Yes.
Now, when these sites get close together, you're going to get interference between the two sites, and I've done some stuff which suggests that might impact the pressure profile as these impacts get close together. And there's some work done on sort of a periodic array of impacts. And I'm just wondering about whether assuming that each local site is a microcosm of the sort of the Wagner impact is a conservative assumption, because I don't actually think it may be that actually having these sites close together will increase the pressures.
That is true, and well, we've looked a little bit at that. Let me see if I can find. Let me. I must maybe look at the hidden slides here. So this is, for instance, I think you can see it. So this is a pressure map of two two crests just impacting very closely to one another and entrapping a little bit of air in between. So this is the two impacts. So these are the Wagner responses, and this is the oscillation of the air pocket in between. So that's something. Indeed, of course, they will interfere. That's clear. And however, if you are, of course, interested in the pressure peaks, they are generated very much at the point that they impact. But there could also be a time. So if there is a spatial shift between the two crests, then they will also impact at a different time. And may, for instance, already happen that one crest has already wetted the area where the second crest is going to impact, and these things are definitely going to be of importance. But leading order, this is what you will see. That's the point that I wanted to make. Yeah.
Thank you.
Yeah, impact configuration could be very complicated, and this is just 2D, by the way. So if to make it 3D, then it would be
exactly.
It would be terrible. And could be last question. We are already behind the schedule, but just one question. You mentioned phase change, physics connected caused by phase change. And but phase change, as I understand, it's mainly it's not about bubbles, but about evaporation, condensation, right? When
Yes.
the LNG you mentioned, it's converted to the vapor, and vapor return to LNG, and that is could be related. I mean, phase transition could be related to the pressures, which are rather high by impact. So if
Yes.
in other places of the tank there are nothing happening like this, but in the place of impact, it's possible that there is a conversion of liquid and gas one to
Yes.
another. So do you think this is really happening? Because it's
I don't know whether that really happens. So to be honest, we're looking at these things. We're doing experiments where we impact droplets in equilibrium with their vapor onto a surface and onto a heated surface. We haven't found any evidence that there is a large influence of the vapor layer in between the droplet and the solid. But what we do know from Leidenfrost experiments that have been done also in our group, where we impact water droplets or ethanol droplets onto a heated surface, is that there is a huge effect of the vapor being produced. No, it's simply a matter of how much vapor is being produced and whether it can interfere with the impact or not. That would be my answer. And it depends a lot. It depends also, of course, you could also imagine that in these large LNG vessels that there are large temperature gradients also in the walls, and that there where the wave hits, that the temperature is much higher than the boiling point, in fact. And then you would get something like a Leidenfrost impact, if you want. Yeah.
Thank you very much. Thank you very much, Devaraj. Just first, thank you. And then just to remind to our participants that in 2 weeks, not in 2 weeks, actually 3 weeks, there will be a presentation by Jose Gargillo on droplet impact on the heated plate with a count for that vapor that I mentioned at the end. And then on 23rd, there will be a presentation by Limarchenko. It's about sloshing. I don't think there are many impact cases, but it's still about sloshing, which is a very complicated phenomenon, and it's studied from different sides. But all of them, they are, related, and this is very complex with each physics behind. So if there are no other questions, so then I stop recording. I stop recording first. Yeah, and